Hi all, welcome back to the memory management series of operating system. In last some videos, we learned about the various non-contiguous memory allocation techniques, among which we learned about paging and discussed how paging gets implemented and solve various number of questions on paging. In this video, we will be learning about inverted paging. Okay, so in inverted paging is also a non-contiguous memory allocation technique, but it is somewhat different than the paging. Okay, so we'll learn about how it is implemented and then we'll be solving some questions based on that. So let's see what is this inverted paging. So we all know the CPU doesn't generate a physical address. Okay, so CPU generates something called the logical address. Now, what is this logical address? This logical address consists of a particular page number and a page offset. Okay, so let's say this is our logical memory, or it's better to say our virtual memory, secondary memory, or whatever you call it. So let's say our this is our secondary memory, and let's say it is 8 kilowatt. So this is 8 kilowatt. Now it has been paging has been applied onto this, and let's say that page size, since we are learning of the paging, let's say the page size is 1 kilowatt. Okay, so it is divided into some sections, 8 sections. Okay, and each having some page number. So let's say this is zeroth page, this is first page, this is second page, this is third page, this is fourth, this is fifth, sixth, and seventh. So altogether there are 8 pages, and each page size is 1 kilowatt. So in this there are 1 kilowatt, such that like this. So this is 0, 1, 2 up to 2 raised to the power 10 minus 1. I think it is a little bit, we need to shift 2 raised to the power 10 minus 1. Similarly, so like this, paging has been applied, and here one word is stored. So this is one page in with page number 000, I mean 0. This is one page with page number 1. This is one page with page number 2. Inside that page we have our instructions, and let's say these are the rows of this particular page. So that is 2 raised to the power 10 rows, and in each row we have one word of information, because the paging has been applied onto that. Now this is our virtual memory. The CPU generates this address. Let's say the CPU generates a logical address carrying 13 bits. Let's say it's 3 bit and it's 10 bit. So whatever 3 bits denotes this page number, and 10 bits denote the page offset. In this page, where is our information present, where is our instruction present. So this denotes this. But from this, CPU cannot access directly the virtual memory, because these pages are being bought into the main memory, right, in the form of frames. This is the main memory, and let's say it is 4 kilowatt only. So here also paging is applied, and there are 4 pages that are being brought from the virtual memory to the main memory, and each page or each frame is having a particular frame number. Now let's say this is one page, that is first page is bought here. So P1 is bought here, P3 is brought here, P4 is brought here, and P7 is brought here. Okay, so out of this 8 pages, 4 pages are present in this main memory. Now if the computer generate I mean if the processor generates the logical address, that is the address of this, and our pages are stored in the main memory at certain other address, then there has to be some address translation between these two. So in paging we discussed that for each page of this logical virtual memory we have the corresponding frame number. But here we are discussing of the inverted paging, so let's focus on to this. So in inverted paging, what happens, we have definitely we will be having one page table, but in this page table we will be having the entries different. For example, in this page table, for each frame we will be having the corresponding page number. Okay, so here we are storing the frame number, and here we are storing the page number. Okay, apart from the page number, there are some entries like the process ID or so. Okay, so here is the frame number, let's say 00011011. Okay, so these are the frame number, and corresponding to each frame number we have the page number. Let's say in 00 the page 1 is stored, so we will write it like this. In the page frame 1 we have the page 3 stored, so it is like this. In page 2 we have the page 4 stored, and in page 3 frame 3 we have the page this stored. So it is mapped like this. So that is why it is called the inverted paging, because here we are storing the frame number. For each frame we have the corresponding page number whatever is stored in this frame. Okay, and apart from that we have the process ID. So each page is referring, I mean each page is associated with which process. Here we will be mentioning, like it is associated with process 3, it is associated with process 2, it is with process 1, this is with process 7, like that. Okay, so this is our inverted page table. Now why it is called inverted page table, we understand, because in page table, in paging we saw that here is the page number and here is the frame number, but it is just opposite. That is why it is called inverted page table, or you can also call it as the frame table, because here we are the entries, the column, or you can say that the indexes are the frame. Okay, so now what happens that the CPU generates this logical address. Now let me change this color so that it doesn't. Okay. So now the CPU generates this logical address, and we want something called the physical address, so that we can map, take out this page from the physical memory. So we need the frame number and the page offset. So this will be obviously same 10. We want the corresponding frame number with this page number. Okay. So now what will happen? The CPU will be looking into this frame table. So let's say it wants to access let's say page number 3. Okay, so it wants to access page number 3. Now what will it see? It will see here that where is this page number present, and what which process we are looking into. So what will happen? It will be seeing in the form of page number and process ID. So the request will be coming in the form of page number and process ID. So for some process ID and for some page number, it will be looking inside this inverted page table. So it finds that page number 3 associated with process ID 2 is located at frame number 1. So from here, it will be getting inside, and it will be converted into page number 1, sorry, frame number 1, and then from here it will look into this physical memory to fetch this page. Okay, so in this way the mapping happens. So just the differences here is that this is the frame number and this is the page number, and along with the page number, the process ID is also present, which process is using this page number right now. So this is an important thing here. Apart from that, everything remains the same. So this is all about inverted page table. Now we'll see what is the use of this inverted page table, why we go for inverted paging, and what is the significance of this. So what happens that in paging we were having a page table for all the pages, even though those pages are not present in the main memory, we were having the entries for that, whether it is a null or empty, but we were having the entries. So first thing, to avoid the overhead of maintaining a large page table, to avoid the overhead of maintaining page table for every process, because for every process we were having one page table, right? So for every process we were having one page table, so it was an overhead. Right here if you see, it is page number is allocated, is associated with the process, whatever processes are running in the CPU, accordingly that page number has been brought here, right? So to avoid the overhead of maintaining page table for every process, inverted paging is implemented. Inverted paging is implemented. Okay. And in inverted paging, only one page table is maintained for all the processes. So that is a very good point, that in inverted paging, in inverted paging, only one page table is maintained for all the processes. In inverted paging, we have just one page table, and in that we are maintaining the process ID which is associated with each of this page table. So only one page table is maintained for all the processes, right? So these are some of the important point, and the very important point is here that number of entries, which we already have seen in the inverted page table, is equal to number of frames in the PAS. Number of entries in the inverted page table is equal to number of frames in PAS. Okay, so this is an important point, that number of entries in inverted page table is equal to number of frames in the PAS, right? This is very important. There in paging, it was number of entries in the in the page table is equal to number of frames in the LAS, but here it is equal to number of frames in the PAS, right? Because frame is being mapped to page, right? And the second thing, that we are avoiding the overhead of maintaining page table for every process. So for all the process, we have altogether only one page table, right? So the memory to maintain page table for processes will be less, but the searching time for corresponding process will be more, because here if you see, when the CPU generates this address, so here it is the page number, so you have to go through all the entries to search for this page, right? And if it has been here the page number, then it could have been just one, with the index you could have search it, but here you have to go through all the entries to search for this, right? So there is this overhead coming up. So although the memory to maintain page table, to maintain the page table for the processes is less, to maintain the page table for the processes is less, but the searching time for each page, searching time for corresponding page, for corresponding page will be, for the process, for a particular process, for a particular process will be more. Okay, so this is one demerit, because we have made the index as the frame number. So we have to go through all these entries of uh, the frame table so as to get our desired entry, that is this page number and process ID. So this is what we are searching, and for that we have to go through the entire frame table to look into which frame is associated with this page number and process ID. So that is why the searching time will be more. However, the memory located for maintaining just one page table for all the processes is less. So this is one thing. Now let's see some of the questions that will come on to this. So let's say we have a system, and this system has a logical address LA equal to 34 bits, and then we have the physical address as 29 bits. Okay, and page size is equal to 16 kb. Okay, and memory is of course byte addressable. Memory is byte addressable, right? Now if the pte is equal to 8 byte, Then we are asked that if conventional page table is applied to this, if conventional page table is applied to this, then calculate the page table size. Page table size. So let's say if we are applying the conventional PT, so for the page table size is equal to number of entries into entry size, right? And the number of entries is equal to number of pages in the LAS, number of pages in the LAS into entry size. And what is this entry size? Entry size is nothing but the uh, frame bit, or frame bit, right? Number of bits used to represent one frame. Okay, so let's say number of first find number of pages in the LAS. Okay, PT is already given, right? 8 byte. So we can just multiply it by 8. So we just need to calculate number of pages in the LAS. So number of pages in the LAS will be LAS upon page size, right? So LAS is nothing but we can calculate from here 2 raised to the power 34 byte. Okay, and what is the space size? Space size is 16 kilobyte. Page size is 16 kilobyte, that is equal to 2 raised to the power 14 byte. Okay, so it will be something like 2 raised to the power 20. So number of pages is 2 raised to the power 20, and entry size is 8 byte. So we can say 2 raised to the power 23 byte, that is equal to 8 MB. So when we are using the conventional page table, then we have the page table size as 8 MB, right? Let's say if we are using inverted page table. So if we are using this inverted page table, then what happens? That page table size is equal to number of entries into entry size. Entry size, let's assume this the same for both, that is 8 byte. But here the number of entries will be changed. It is equal to number of frames in the PAS. Okay. So number of frames in the PAS is equal to PAS, physical address space, by frame size, and frame size is nothing but the page size. So into 8. So PAS is equal to if you see from here, PA is equal to 29 bits. So PAS is equal to 2 raised to the power 29 byte, and the page size is equal to 16 KB. So it is 2 raised to the power 14 byte. So altogether it comes as 5 and 1, 2 raised to the power 15 into 8, and that is equal to 2 raised to the power 5 plus 3, how much? 8. So 2 raised to the power 18, and that is equal to I think 2 raised to the power 8 is 256 kilobyte. So inverted page table size is 256 kilobyte. So see how drastically the memory has been reduced from 8 MB to 256 KB by just using replacing the conventional page table with the inverted page table, right? So this is what we want to discuss in this video, so that if we are using the inverted page table, the memory that is being allocated for the page table, the overhead of maintaining page table for every process is drastically reduced by using inverted paging. And we need not to maintain the page table for all the processes. Just only one page table we will be maintaining for all the processes. But there is a side effect of using inverted page table, is that searching time for the corresponding page for a particular process will be more. Okay, so this is one point that we need to think about in this case. Then I think we are done with this inverted paging. Next video, we will be seeing some more non-contiguous memory allocation technique. So till that, keep watching. And if you do have any doubt or any comments or any questions, please post into the comment section. I'll be happy to help from there. Thank you very much.